We talked about different types of counters, ripple counters, synchronous counters, up count, down count, non-sequential counters, where we let the processor go, let the circuit go through states which are not in sequence. All of them use flip-flops. We basically understood the characteristics of flip-flops. So using the characteristics, we can design any of these counters. And the next step from counters is registers. The other day I introduced it briefly. A register is set of flip-flops. A group or bunch of flip-flops. They usually have a common clock. So typically it looks like this. Let us say it's a D flip-flop. This is a 4-bit register because there are 4 flip-flops. It will be a clock. Even though the clock is shown here, it is individual flip-flops which get the clock like this. I am showing all these 4 together. But basically these are D flip-flops. Q of this goes to next D, Q of this goes to next D, etc. And all of them are clocked at the same time, like synchronous counters. The use of these flip-flops, these registers, is to store any data that you want. So whatever you give as inputs, these are the D inputs. And outputs are Qs. You give a set of inputs to the D inputs and clock it, the positive edge triggered clock I am showing. So these data points, these data get stored in this flip-flop. These are basically storage devices. The flip-flop is a storage of 1 bit. So this is 4 flip-flops, so it is a 4-bit register, stores 4 words, 4 bits, and once it is stored, it is available here. I can read it by tapping these Qs, but when you read it, it does not destroy the content of the flip-flop, D flip-flop. So as long as I keep the inputs and clock it, the same inputs are available, these inputs are available in the flip-flops, and these can be read. Just because you read it does not mean you are destroying the contents of the flip-flops. If you want to change the values here, you can get another set of values, and at that time new clock is, after that the first clock cycle, positive edge, will take the new values into these flip-flops and they will be available in the output. So as long as the inputs are kept and it is clocked, outputs are available. Now if you want to clear the whole flip-flop, make it all zeros. So we have you know that each of these flip-flops has a clear input. Which makes this output 0. So I will show it as one single line which goes to all the flip-flops. When you apply a clear signal with a negative we put here, when you make clear 0, they become 0. After that if you want to change the inputs, you can get a new values here, you should remove the clear. You should keep the 0 of the clear only. As long as you keep the clear 0, this will remain zeros. But if you want to give a new set of values to the flip-flops, then I should remove this clear and make it high. It is low, clear, high, Q becomes input. Sometimes there is an extra input called load input. This load input is to absorb the contents into this. So you can design a flip flop such that only when the load is effective, that means you clock this load and clock at the same time. So when the load is high or low depending on what you want, then the inputs will be stored here and they will remain stored there, and as I said, the clock will keep on coming, outputs will keep on having the same values. This is a register. Register is used for storage purposes. A memory consists of all registers. So the 4-bit is too small. You want to store an 8-bit word, I need an 8-bit register or 16 bits, whatever is the type of registers available. These are registers available on market, 8-bit registers, 16-bit registers, so forth. Now one improvement of this registers, register is simply for storage. You give the inputs, clock it, the value gets stored in these flip flops, they are available for you to read them anytime you like, as long as you do not clear it or as long as you do not load it with a new set of values. An improvement over this is called a shift register. We talked about it also briefly the other day. In the shift register, again is set of flip flops. Here you clock it, each clock, this is D input, Q output. This Q is connected to the D of the next flip flop, and this Q, this D, this Q goes to this D, and this is a Q here. So there are 4 bits or 4 flip flops. They are also clocked at the same time. So when you clock the first flip flop, the input here, suppose you give an input here, instead of parallel inputs of all the 4 flip flops having different inputs at the same time, I give only one input to the first flip flop, then this clock takes this value into this. So in the next clock cycle, this Q travels to this flip flop. This Q gets stored in this flip flop. In the next clock cycle, this goes here. In the next clock input, this goes here. And the next clock, this goes out. You lose the data. Suppose I have 0 here or 1 here. I will call this ABCD. I start with the 1 SI, 1, outputs are 0, 0, 0 for other 3 flip flops. After the first clock, takes this 1 to the next level, then 0 gets bumped into this 0 goes into this, and this 0 goes out. And what will happen here depends on what you have in the input. Supposing I do not give anything, it will again become 0. Supposing I take this 1 remove this one and put a 0 at the second clock, this 0 gets input into this. So, now this 1 goes here, this 0 goes here, this 0 goes out, this 0 goes here, and then this is a 0. Third clock, this 0 goes out, this 1 goes here, this 0 goes here, this 0 goes here, this becomes 0. On the fourth clock, this 1 goes out, this is 0. So, you start with 1 1 1 1 0 0 0, and you want this, that it happens finally after 4 clock cycles. But of course, I can always change this SI. It does not have to be 0, I can have some other value, and that will come. For example, I can have 1 1 0 0, this becomes after the first clock, and I can also take this back into this input. This is called recirculating feature. So, when it is bumped out, it does not go out, it goes to the first position. So, this is the initial value after first clock cycle. This 1 goes here, this 1 goes here, this 0, and this 0 goes back into this. After second clock, this goes here, this goes here, this 0 goes here, and this 0 goes into this position. Third clock, this 1 goes here, 0 0 1. After fourth clock, it is 1 1 0 0. So, after 4 clock cycles, I get original value back. I want to keep this 1 1 0 0, I do not want to destroy it. So, I connect it to the shift register and keep shifting it so that it always remains inside. After every 4 clock cycles, I will get the original value back. This is called as shift register serially input. This is called serial input, serial output, because input is given to the first flip flop, output is taken from the last flip flop. This is called serial in, serial out, shift register. Whether you want the recirculating feature or not is up to you. You do not have to have it. If you do not want to lose the data, keep it recirculating. Then this is used for delay. Supposing I have this value and I want this value to come after 4 clock cycles of delay, this can be used for this purpose, used for delay. Then I can have serial input, parallel output. What happens is, I give input, I take here, 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 all the same. So, a series of 4 pulses I give, and the 4 pulses will appear here, 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 and I can read them all simultaneously. After 4 clock cycle, I want to read them parallelly, all of them. So, this is for serial to parallel converter. Supposing I want to 4 inputs I give serially, and I read all 4 flip-flops at the same time. Third is parallel input, serial output. I give all the 4 flip-flop inputs at the same time, but take one at a time. This is called give all 4 bits to 4 flip-flops at the same time, but read the output from the last flip-flop. That means I can lower something and take one at a time. This is a parallel to series conversion. Serial to parallel conversion, this is just for delay. And fourth is parallel input, parallel output. I give inputs all at the same time, take outputs all at the same time. This is the memory used as memory. That is how you have different types of shift registers. So, we will give a simple example of what we can do with this shift register. Suppose I have a circuit like this. I have a 4-bit shift register. I will call this shift register A, whose input is taken from the last. I also connect this is serial input, serial output. I also connect this to another shift register whose SI is this and SO is this, serial output. I clock them all at the same time. But this clock is also gated through a, this is the clock, and a shift pulse. So, only when the shift pulse is high, the clock reaches here, otherwise the clock is not there. So, whatever you put there will remain here, and there is nothing going to happen here because this will go here. Now, this is the clock. Clock is a function of t. A function of time. Now, I am going to give a shift pulse which is a 4 clock cycles duration. One, two, three, 4. This is the shift pulse. So, these 4 clock cycles are the ones which are available to the 2 clocks. Even though there is a clock here, this is continuous clock, because the shift pulse is here, the shifted clock or the clock is enabled only during this period. That means during that period we are giving 4 cycles, and these 4 cycles will go here and recirculate it. So, once that happens, what happens is this SO also goes into this first clock cycle. For example, you write here 1010 was the original value, initially value. After the first clock pulse, shift register A, B we do not know, B can be 0, 0, 0, 0. I will call this A and this B. Under first clock of this gated clock. So, this is what I call 1, 2, 3, 4. First clock, second clock, third clock, fourth clock. After the first clock, so what will happen? This 0 would have gone here. After second clock, 1 comes here, it would have become 1, 0, 0, 0. After third clock, this 0 will go here, 0, 1, 0, 1. So, this 0 would go here, so it will be 0, 1, 0, 0. Fourth clock, this 1 goes here. So, this 0 would be 1 goes here. So, A and B will be same value. So, I have 2 shift registers A and B. A is a recirculating shift register with serial input, serial output. The serial output of A I give it to B as input and take the output here, B. Now, I clock it, but not always. I clock it with a gated, with a gate which is AND gate. So, whenever I want the shift operation to take place, whenever I am ready to receive whatever I put in A, whenever I am ready to receive in B, at that time I give the shift pulse, but the shift pulse will be of 4 clock cycles duration. So, after you give this shift pulse, I will have 4 clock cycles. During 4 clock cycles, both the registers will be active. So, this is recirculating. So, I go from 0, 1. This goes here. After 4 clock cycles, I get the original value back. This is my first value, same as the last value, and earlier we did not know what was inside B, so I assume all to be zeros, and after 4 clock cycle this one comes here. So this is what I meant by delay. So I can have a 4 clock cycle delay in B output, and I do not lose my data, it keeps circulating. Since it is circulating all the time, I keep the data here. So whenever I have a need to use the data, I have to apply a clock cycle along the shift pulse, and at that time I will receive the 4 bits output of second register as so. So this is basically a shift register. There are 4 types of shift register what we saw. What is a shift register? It shifts data from one flip flop to the next with every clock cycle. I can have the data back by recirculating it, and I can also 4 versions of that. I can give input serially and take output serially, that is for delay purposes like this. This is an example of that. I can have serial input and parallel output, where I give all the inputs one at a time, but wait for 4 clock cycles and take the output. That means the serial data is converted as a parallel data and we read it. Third one is parallel input serial output. I give all the 4 flip flops at the same time the data, but I take one at a time as output by shifting it. So that becomes parallel input serial output used for parallel to serial converter. Finally, I can give the data parallelly inputs, also take the data parallel output. I do not destroy the data as long as I do not clear it or I do not put a new value of load, new value and load it. Load pulse will be used to put a new set of values. If I do not use the load, whatever I put will be remaining as long as I do not clear it. In that case, this is whatever I put remains there and I can read it anytime I want. This is a memory. In memory what you do, you put something in the memory and read it off whenever you want. This is parallel input, parallel output. These are the 4 types of shift registers, but in general we have only seen one example, all shifting right, goes from here to here, here to here, here to here like that. We can also have a shift in the opposite direction. So we have what are known as universal shift registers, which are available commercially in the market. You can go and buy a universal shift register. So, in universal shift register we have left shift, the data can be shifted 1% to the left every time. You can have a right shift. I can clear it, I can load it, a new value can be loaded anytime I want, and then you can shift it to the right or the left. I can clear it anytime I want. Then of course there is a clock requirement. clear, load, clock. Load can be parallel load. When you say load, usually it is parallel. Otherwise, you can shift it, put the data in serial mode. This is serial mode. So, serial input, I will say. You do not need a load for that. Serial input you give and shift it every time. Or you can have the data without change, no change. So, in other words, there will be one shift register I can give input, serial input, here goes like this, or I can give the data here, this is serial out, I can give the data here, move here, this is shift out, this is what I call right shift. This is what I call left shift. As I said, you can always clear the whole thing. I can load it. Load means this is so new value can be loaded anytime you want by putting the value here. This data can go into this. So clear, clock, of course, whole thing has to be clocked. There has to be clocked, that's a serial input from the right, from the left goes to the right, serial input from the left goes to the right, or I can have a loading parallelly and then you can shift it right or left again. I can clear the whole thing when I do not want, and of course output can be serial or parallel. This is parallel output. These are serial outputs. This is SO and SO. Such a register is available commercially. You can use it to put it to any use you want by buying a 4-shift register. So you have I have a 4-bit universal shift register or an 8-bit universal shift register. So I said there are lots of uses for the shift registers, these 4 uses. Also they are used very much in other digital circuitry. We can use shift register to design counters. We can use shift register to design serial adders. Whenever you want something to be shifted, suppose you want to multiply 2 numbers using an adder, you can do this. Single adder, you put the numbers one at a time, 1 bit at a time, and shift it so that you can get the multiplication completed. There are other applications, but there is one application which is generally very useful is suppose I have a 4-bit shift register. serial input, parallel output, SR. With a right shift. It means whatever I put here will go here to here, here to here. This is called right shift. And parallel out means I have outputs here. I give input here, outputs I take here. So this is a serial input parallel output shift register with a right shift. And now I connect two of these outputs to an exclusive OR gate. Give the output of this as the input to the shift register. So I have an initial value of anything you can have. You can have 1100 initial value. By parallel load you can have, or you can have serial input and clock it 4 times. Of course, the clock is required. Now these last two outputs, so you want to call this A, B, C, D. The CD are connected to a shift exclusive OR gate and back to the shift register input. So when you do this, when you get 0, 0 here, the output is 0. For an exclusive OR gate, you know this truth table. Okay. Now when I have 0, 0 as input to the two inputs of the exclusive OR gate, I get a result of 0. So now what will happen? A becomes 0 because I am putting it here. This one will go here, this one will go here. Everything gets shifted by one position. This 0 goes out. This one goes here, this one goes here. This 0 is the output of the exclusive OR gate. Again, I do this repeatedly. This is the first clock, after clock 1. After second clock, this 1, 0 will become 1, 0, 1, 1. After this clock, 1 will become 0, 1, 0, 1. Next is again 1, 0, 1, 0. This 1, 0 becomes 1, 1, 1, 0, 1. Becomes 1, 1, 1, 0. 1, 1. This 1 becomes 1, let that it keeps on going. Every time a new pattern is coming. One makes it 10 makes it 1, 0, 1 makes it 1, makes it 1, 1 makes it 1, 0 makes it 1. So this 1 will make it 0, this will make 0, this again will make 0. See, every pattern is different. Keep on giving clock cycles, each time you get a different pattern. Now it becomes 1, this is what I gave in the first place. After so many patterns, the original input is restored, and what order it comes depends on what is the initial value you give in the shift register and which two outputs do you connect to a exclusive OR gate. So depending on the inputs of the exclusive OR gate and the original pattern, I get the whole series of patterns, each time is a different pattern. If the initial value is different and the taps are different, instead of CD I take BC or AD, anything. Depending on which two outputs you take and depending on what is the initial value, you get this. So this is called a pseudo random sequence generator. How many cycles it takes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 cycles it takes before you get the original value in a 4-bit shift register. You can have a 5-bit shift register, it will be even more fun. 31 patterns will come. 3-bit shift register, 7 patterns will come. This is used in communication. Suppose you want to give a pattern which is random, you put arbitrarily some value, the initial value, and give any two inputs as the, any two outputs as the input to the exclusive OR gate. Why is it called, it is a random sequence generator. Why is it called pseudo random? Because you can predict it at the most, you can only have 15 variations. 16th variation will be same as the original variation. So it is not all that random, it is somewhat random, that is why it is called a pseudo random. This is a very good application of a shift register. So I have done completed shift registers. We started with the registers, of course we started with flip-flops, different types of counters. We talked about ripple counters, synchronous counters, up counter, down counter, a counter which can be decayed counter, a counter whose count can be terminated, or we also talked about non-sequence counters, non-sequential, that they can assume any sequence that you want, and how to use these things, how to build these things using flip-flops, using the characteristic equation of flip-flops, all that we have seen. And then we went to registers, which are basically group of flip-flops used to store data. You give the data input, remains there, take the output. If you want to change the data, if you want to clear the data, you can do a clear. If you want to change the data, you put a new value and then load it. All that we saw. Then we saw shift registers in which the data keeps shifting from one position to the next position. There are different ways. You can give the serial input, serial output. You can give serial input, parallel output. You can give serial input and take parallel output. We can give parallel input and serial output and parallel input, parallel output. Each one has its own use. And we saw universal shift registers where you can do a shift of give the data serially in on the left hand side, shift it to the right, or give the data serially to the on the right hand side, shift it to the left, or you can give parallel data input, load it. You can have a serial output or a parallel output. You can load it, you can clear it, all that is possible. It is called universal shift register. 4-bit shift register available, 8-bit shift register is available. Then we saw one application of a shift register which is used as a pseudo random signal generator, sequence generator, because we give an arbitrary pattern in the input at the initial value of the shift register and then take the two outputs, feed it through an exclusive OR gate back to the input. So it assumes all values. It is a 4-bit register. If you take the last two outputs as the inputs of the exclusive OR, it takes 15 patterns before it returns to the original. By changing the pattern in the initial pattern and changing the tabs, you can have different sequences. It is called a pseudo random sequence generator because it is random to a certain extent, but not completely random because after some time it repeats. That is why it is called pseudo random. This is the sort of end of this chapter on flip flops and registers, shift registers, all that. Next we will have to move on to other sequential circuits. For example, registers and counters are not the only sequence. We define sequential circuit as a circuit in which flip flop is the basic building block. You give the data, it remains there, and the next state depends on the previous state. For example, in JK flip flop, you put 1 1, the output is complement of the previous. So if you do not know the previous, you do not know what is the next one. So that is how we started with sequential circuits. We talked about latches and then flip flops are different types, SR, JK, D and T, and for each one of them we looked at the behavior called characteristic table, also wrote the characteristic equation, and we used them in counters as we saw. Now we have to also see other applications of flip flops or so general sequential circuits. Sequential circuits not limited to counters and registers. We will see. For example, if you have an elevator, how does it work? How do you design it? What are the various states in the elevator and how it goes from one state to the next, and how do you define it, design it? Like that there are other applications. Supposing you have an input pattern and require a particular output sequence, how do you define it? So these are general sequential circuits design. Also called state machines, FSM stands for finite state machine. This term machine came about because those days everything was a machine. do not think it is going to be a huge machine, it is a circuit, digital circuits. State machine means this machine or the circuit assumes different states, and finite means it has only a finite state number of states, you do not have an infinite number of states. For example, 8-bit counter, I mean 3-bit counter will have 8 states. It is a state machine because it goes from state to state. Even a sequential circuit even a counter which goes from 0 to 7 back to 0 can be called as a state machine because, for example, a 3-bit counter, up counter, I will call this S0, S1, S2, S3, S4, S5, S6, S7. S stands for state. State 0, state 1, state 2, 3, state 4, 5, 6, 7. There may not be anything very significant. This can be 0, 0, 0. From there it goes to 0, 0, 1. It goes to 0, 0, 0, 1, 0. It goes to 0, 1, 1. Goes to 1, 0, 0. Goes to 1, 0, 1. Goes to 1, 1, 0. 1, 1 and back to 0. This is also called a state machine. Machine is something which you do not have to bother about. They called it machine because anything that works like this based on an input, because those were days where mechanical engineering was prominent and everything they did. Computer was called a computing machine. Everything was a machine. So that is why it is called machine. Do not worry about that word machine. It is a finite state circuit. Why is it state circuit? Because it assumes different states. Why is it finite? Because there are only 8 states. This is easy because we already know how to design this using flip-flops with edge triggered flip-flops, using JK flip-flop. You know how to do it, we have done it also. All of these are synchronous counters, by the way. No asynchronous here. Synchronous machines. So these are synchronous machines or synchronous count design, synchronous circuits I will call them. So don't be worried about the term machine too much. Let us take an arbitrary circuit, 5 states. This is a 5-state circuit or a machine again. 5-state circuit, finite state, digital circuit, sequential circuit, synchronous. So let us say it goes from here to here, there is a circuit with an input X, and this is the state machine with 5 states. We will define X is 0, we will shift up, count up. This is an up-down counter, let us say. Only 5 states, not 7 states. X0 will count up, X01 will count down. So I will call this 0, 0, 0 state, 0, 0, 1 state, 0, 1, 0 state, 0, 1, 1 state, 1, 0, 0 state, and back to this. So if with X is equal to 0, it goes from here to here. X is the input. If x is 1, goes from here to here, from here to here, from here to here, here to here, here to here. I made a very simple circuit to give an example of a state machine and how it is designed. There are 5 states whose they are designated as 0, S0, S1, S2, S3, S4, and they have 0, 0, 0, 0, 0, 1, 0, etc. because we need 3 bits. If it is 5 states, I need a minimum of 3 bits. Up to 4 states, I can have 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. 5 states, I need 1 more. So now, how do I know how to design this circuit? I will write what is known as a state table. The state table will show you what are the various states, S0, S1, S2, S3, S4 are the presently they are. If the circuit is in state S0, if x is 0, what happens? X is 1, what happens? S is 0, it goes to S1, S1 goes to S2, S2 takes you to S3, S3 takes you to S4, S4 takes you to S0. Because x is 0, goes from here to here, here to here, here to here, here to here, here. S4 will take you to S0 again. X is 1, S0 will take you to S4, S1 will take you to S0, S2 will take you to S1, S3 will take you to S2, S4 will take you to S3. This is called a state table because this tells you what are the present state and what are the next states for this is present state and next state when x is 0, when x is 1. Now, we already designated S0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0. So, we do not have to keep S0s, we can keep as, we can rewrite this table. State table becomes, can be rewritten with binary values for S0, S1, etc. So, this will be present state is S is S0 is 0, 0, 0 and if the input is x is 0, next state is S1. The present state is 0, 0, 0, the input is x is 0, next state is 0, 0, 1. If the input is S0, 0 again, but x is 1, what happens? X is 1, it goes to S4. X is 1, it goes here. So, S4 is 1, 0, 0. So, I have to complete this table. S1 to S2, S1 to 0, S2 to S3, S2 to S1, if x is 1, S3 to S4, if S3 and x is 1, takes you to S2, on S4, 1 0 0, input is 0, goes back to 0 0 0, otherwise it goes to 0 1 1. So I have here a table which tells you what are the present states and what states they assume next based on the inputs. So I like to have some variables, S 0 0 0, 0 0 1 and all that, we give some variable names. We will call this ABC, and next state we always call A plus B plus C plus. That is just tell you it is next state. A plus does not mean anything, nothing like A plus here. A plus is if the circuit has an A as the input 0 and the input is applied, it goes to A plus next state. Now I want to find out what is A plus, B plus, C plus, and once you know that, we know D flip flops, DA, DB, DC, which are following the cues. I don't need this anymore, this diagram. So if this is the case, what will be DA, DB, DC? This is 0 1 0 0 0 0 1. This is DA, DB is same as B plus, next state of B is DB, which is 0 0 1 0 1 0 0 1 0 1, and DC is 1 0 0 0 1 1 0 0 0 1. This is same as this. This is identical to this because we know that characteristic equation of a D flip flop is D is Q. So DA is A plus, DB is B plus, DC is B plus, C plus. Plus does not mean anything. Again, I want to emphasize this point. Plus is to tell you it goes to the state A, goes to state present value of A has a new value called A plus after the input is applied to the next clock cycle. So the present value is ABC, next values are A plus, B plus, C plus, that is given by DA, DB, DC. So I have to draw corner maps. The procedure is now simple, we know how to do design counters using JK flip flop, D flip flop, etc. Same procedure will now be followed. So I will have corner maps whose inputs are A, B, C, X, this is A plus, or A plus, then you can have B plus, and C plus. So, you map these values 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. How come? There are 5 into 2, 10 values there. 1, 2, 3, 10 values will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. And rest are don't care because we don't have those states. This will be 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. Rest of them we don't care. And finally, DC would be 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. Don't care, don't care, don't care, don't care. Oh. Now, these are corner maps, you know how to read them. You write the values. A plus would be, see, I have no use for these things because this is separate, unique. These two can be combined. So, A plus would be A bar, B bar, C bar X plus B C X bar. B plus would be, I can fortunately combine these two, and these two. Oh, there's one here. This one is this one, this. Are there 4 terms here? B plus. Zero, 0, 1, 0. Right. 0, 0, 1, 0. Correct. So, we have one term here which is B C bar X bar. This term is B bar C X bar. This term is A x plus this term is b a b c x b c x b c x bar c x a x. Okay. Then C plus would be these four, these four, these two, these four would be A x, these four would be B C bar, these two will be A bar C bar x bar. That's all. We have all the three equations. We can draw the circuit. It takes 3 flip-flops. I assume D flip-flop. We can do the same exercise with JK flip-flop. 3 flip-flops are there. 1, 2. I'll call this DA, DB, DC. All are clocked at the same time. This Q is Q bar, Q bar, Q bar. This is A bar, B bar, C bar. So you can connect now. Do all these equations. I am not going to draw this. I will draw one to make it simple. For example, C plus would be AX, A is here, X is input, AX, BC bar, A bar, C bar, X bar. Only X needs an inverter because X is an input. Is X bar. All others we have inverters here. A bar, B bar, C bar available. So this connected to an OR gate. You give you DC. So you can finish the other two circuits. Just you have to draw this circuit using gates, this circuit using gates. That's it. Now, as I said, this is only D flip-flop. Instead we are asked to do JK flip-flop, you have to write JA, JB, JA, KA, JB, KB, JC, KC. There will be 6 equations, 6 maps, simplify them, and you can draw the circuit. This is how you design a general sequential circuit. We have no inputs. In this circuit we have only states going from up or down from 0, 0, 0 to 1, 1, 1, 0, 0, 5 states. If x is 0, it goes up from S0 to S1, S1 to S2, S2 to S3, S3 to S4, back to S0. If it is x is equal to 1, you grow from S0 to S4, S4 to S3, S3 to S2, S2 to S1, S1 to S0. That is all it is. So, but you can also have an output here. I have not shown any output. Supposing this has this is 0, this is 1, now I am not showing any output, there are only 5 states, 3 flip flops, we call them ABC, we got the present state and the next state based on X, and then we got the equations for flip flops, and then we do this. Now instead I can also have this S0 has an output, I will call it Z or Z as the output, and S2 also. These 2 states are outputs, whereas the rest of them. So Z will be S0 or S2, but we know S0 is 0 0 0 ABC, S2 is 0 1 0. So it is A bar, B bar, C bar, A bar, B, C bar, combine them, this is the output C. This is in addition to the circuit here. So I have these values of A bar, A bar, B bar, C bar. I can use them to get the output. In fact, I can even simplify this because A is 0 on both. So this is A bar, C bar, B plus B bar, and you know B plus B bar is 1. So this is same as A bar, C bar. So my circuit gets, this is my output circuit, gets simplified as A bar, C bar, simple one output, and A bar and C bar are available there, this is output. So I can have outputs, I can use JK flip flops, I can have different states, I can number them a difference, instead of S0 to S4 I can have arbitrary numbering, all that we can do. So this is in general the principle of sequential circuit design. We will see some more examples in the subsequent classes. I would like to stop here. If there are any questions, you can ask me. Are there any questions?
Sir, pattern sequence generator you have used, on the register, after 15 clock pulse, it will give the same value. What is the use of that?
What is that you are asking? I am not clear, it is not clear to me.
Pattern sequence generator, starting value after 15 clock pulse, the same value again produced.
Yeah.
What is the use with that?
I told you pseudo random generator is a random number generation. I want to have a random sequence, but it is not fully random, it is pseudo random because after 15 it gets repeated. See, this random generation is very important signal processing. So they can use this, but it is not fully random, because this is to say, suppose you are sending some signal on the other side, if you know the input side what pseudo random generation is there, the output also they will have the same thing. Otherwise somebody who is not authorized will not be able to make out what is happening. That is the idea. It is returning after 15 because I am using a 4-bit shift register with 2 outputs, 2 inputs to the exclusive OR gate. I can have any number, if supposing I have a 5-bit shift register, and depends on the original pattern as well as the tapping from which I take the output to the exclusive OR. These two decide the pattern. The pattern is not known, that is what I am trying to say, because you will choose what you are going to put as the input values, the initial values, and what are the 2 taps you are going to take is not known to anybody. To that extent it is random. Why is it pseudo? Because after 15 it repeats, or if it is 32 5 bits, it will repeat after 31. If it is 6 bits, it will return after 63. You can have any number you want. Okay?
Okay, sir. Okay, sir. On the A register and B register transfer takes a serial input and serial output. In this way, register transfer takes place or
Yeah.
parallelly register transfer takes place.
No, there are different things. I told you there are 4 different types of shift registers: serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. That is one example using serial input, serial output. That is an example. Suppose you want to delay by 4 bits, or you want the data to be remaining at, you will take it whenever you want, you apply that clock pulse, gating pulse, and take it out. Whenever you want, you have to apply a 4 clocking gate, which is 4 clock cycle duration. At that time you will be able to get the output. So I have this recirculating feature, it keeps circulating. I do not want to use it, I do not have to do it. If I want to use it, I will have to give a clock gate, and that should be 4 bits, 4 clock cycles duration. Then in that case this 4 will go one by one to the next register, you can use it. This is for delaying purpose. Okay?
Okay, sir.
Okay then. Okay then, bye. We will stop here. We will see the other types of sequential circuit design in the next lecture.